zone. So corresponding to this very large length scale, you have a very small Moiré Brillouin zone, and you end up tiling your whole graphene Brillouin zone with this small Moiré Brillouin zones. This corresponds to an inverse scale of 15 nanometer. This, of course, the whole thing corresponds to the original graphene Brillouin zone. Now, in this, if you now change the angle, if you look at the electronic structure in these systems, it's very sensitive to the twist angle. And this is a calculation by Bistritzer and McDonald. This is at 5 degree, you can see bands of about 500 millivolts. And when you go to this magic angle of 1.08 degree, you will see that the bands have to actually zoom this out for you. The bandwidth in the basic bandwidth is about 2 millielectron volts and so on. Now, each of these bands, just to remind you, are 4-fold degenerate. There is 2-fold degeneracy for spin, and there is 2-fold degeneracy for valley, because you can basically expand around this valley or that valley, and that gives you, if for each band there is a 4-fold degenerate bands here. This is the non-interacting picture. Okay, and so if you are near the magic angle, your bandwidth is very low, your interactions will dominate, and you expect very interesting interaction dominated physics in the systems. And when you go and look at it, you can see many different correlated states. I will focus on only one, which is the superconducting state. So here it is. So each band, realize that I told you as a factor of 4. So nu equal to -4 will be emptying out this band. And when we look at nu equal to -2, we see some sort of an insulating state, a correlated insulating state. And if you dope away from this correlated insulating state, people find superconductivity in these systems. These are different. This one is from the original one from Podler's group, and then there are multiple cases where people have found. So this superconductivity is robust. It's found in multiple samples, and so we will start talking about this particular phase, which is the superconductivity in twisted bilayer graphene. Now, you can have other flat band superconductors. You can have multi-layer twisted graphenes where you take a number of layers and twist them by very different angles. One particular one is called the symmetrically twisted tri-layer graphene, where you basically twist you keep the 3 layers, you keep the top and bottom layer fixed, and twist the middle layer by an angle. And once again, this is data from 2022. You see that this also undergoes superconducting. It also has a flat band at a different magic angle, and then it undergoes superconducting transitions as you dope the system. Okay, there are more. There is rhombohedral tri-layer graphene, which again forms a very flat band, and there is a superconducting dome here. You have normal bilayer graphene forming a Moiré structure with WAC2, and that has also, and there are many more which I am not showing. So there is a family of now flat band systems formed by twisted materials, and they also show superconductivity at a certain range of doping. So it's a robust phenomena that is happening here. In today's talk, I will mostly talk about these two, MATBG and MATTG, and not talk much about what is happening in these other cases. Okay, so if I see a superconductor, Bodin, Cooper, and Schrieffer has told us that, okay, there should be some sort of Cooper pair formation, and then there will be condensation of these Cooper pairs. But you can ask more pertinent questions. What is the normal state around which this superconductivity forms? In other ways, you are asking, what is it that you are pairing up? We have some ideas now, and I'll talk about it slightly later from both experiment and theory, about some particular kind of intercovalent coherent states. What is the symmetry of Cooper pairing in this system? What is the spin structure of the Cooper pairing? What is the orbital structure of the Cooper pairing, and so on? By the way, when I say we don't know, it's not because of lack of proposals. Almost everything that you can think of has been proposed. Okay, by someone or other, singlet, triplet, spin valley coupled. This, however, is a sharp question. What is the symmetry of the superconducting order parameter? And in principle, there should be experimental ways to determine this question irrespective of what theory is trying to tell you. And we will, in the later part of the talk, we will talk a little bit about this question, this particular question. Because of course, as theorists, we care about what is allowing the electrons or whatever it is the charge carriers to pair, the mechanism of pairing. Again, not lack of proposals, phonons, spin value fluctuations, fermions, quantum. You can think of anything exotic that has been proposed here. This question, however, is harder to answer because the energy scales in these problems are all almost similar. So that is very hard to do controlled calculations. So on the other hand, so my point in putting this together is that this is a question which should be answerable more sharply. This would be in general harder to answer. Just as a reference for people who know cuprate superconductors, the symmetry of the order parameter there is not in question. People know what it is, D-wave superconductor. Mechanism, of course, nobody agrees on how things have been paired up and so on. And of course, there is another question, is BCS, which is a very weak coupling theory, is it a good description, or do we have a strongly fluctuating superconductor? And if so, what are the necessary, what are their signatures and so on and so forth, okay? And again, since the scales are similar, you will see that if you calculate kf times the coherence length, it's order 1. I mean, it depends on how much. So there are some key questions to keep in mind. And with this, I will turn to the actual paper. And the first part, we will talk about Andreev versus tunneling spectroscopy for flat band superconductors based on these two papers. Okay, so what's the deal? The deal is, there was a set of experiments from Ali Yazdani's group, and what they're doing is they're taking an STM tip, putting it on top of a moire graphene. This is twisted bilayer graphene, and they are pushing it closer and closer to the tip, and then they're calculating the conductance as a function of bias. And so when the STM tip is far away, you see basically a D-wave-like, at least a nodal-like feature, I wouldn't say D-wave. You see that there is a dip and there is a gap that is forming here. Although it's not a complete hard gap, it seems like a more V-shaped gap. But as you go closer and closer, as you basically push it closer, and in the end you just push it into the system, you go into the limit of Andreev spectroscopy, and instead of a gap, you see that there is a excess conductance coming up. This is feet of that excess conductance and so on. Now, what people can do is by fitting all of this, they can extract a gap scale from the Andreev data and a gap scale from the tunneling data. And when they look at it, they see that the tunneling gap is 3 to 4 times that of the gap that you extract from the Andreev scale. And this is a puzzle because in a weak coupling BCS type superconductivity, those scales must be same. Okay, there's no way you can get a different scale from that. And even in the original paper, there was already questions whether this is pseudo gap physics, this is strong correlation physics, and so on, which was suggested. Okay, and so the questions are, why are there two distinct energy scales in Andreev and tunneling? Can one identify one of them as a superconducting gap and a pseudo gap? And if so, the other question is, why is there no signature of this Andreev scale in the tunneling spectrum, which measures the density of states of electrons in the system? Okay. So what we needed to do was to have a theory of tunnel junctions, there's a usual theory called BTK theory based on wave functions, which works in the weak coupling BCS limit. What we did is we actually, and in this case, the junction is characterized by a scattering parameter Z. So Z equal to 0 is the Andreev limit, ballistic junctions. When you are taking your STM up, this is the Z equal to infinity limit. This is in the dominated by single electron tunneling. The weak Andreev limit, ballistic limit is dominated by Cooper pair tunneling, and you can go back and forth between them by depending on how much you're pushing your STM junction. There's another way of parameterizing this by asking for an effective tunneling of the electrons across the barrier, gamma tilde, and Z and gamma tilde has some sort of an inverse relationship. Okay, so what we did is, instead of this BTK theory, which works for weak coupling things. You are asking whether there is strong coupling physics that is dominating. We needed a Green's function best theory for fluctuating superconductor to calculate the tunneling conductance. I'll not go into the details. You can write down the tunneling conductance in terms of what is called the half-space retarded one particle Green's function of the superconductor and the metal. And this basically, we created all this. And this is independent of how strongly interacting your system is. There's no approximation of weak coupling or BCS type things here. When we put that, and then of course, once you know some phenomenological forms for pseudo-gap Green's functions, strongly correlated Green's functions, superconducting, you can put them in. And you can put Green's functions which support both a pseudo-gap scale and a superconducting scale. And what you see is the following. You see that whatever happens, tunneling and Andreev limits show the same energy scales. What exactly happens depends on the model of pseudo-gap that you are putting in. Here is one model which is called a hard pseudo-gap. And here we find that only the pseudo-gap or the single particle gap shows up both in the tunneling limit and in the Andreev limit. Here we see both scales showing up in the tunneling and Andreev limit. These are different models of pseudo-gap. The point being, different things can happen, but whatever happens in the tunneling limit is also going to show up in the Andreev limit. And because the experiments show two different scales in the two different experiments, this cannot explain, a pseudo-gap or a superconducting gap cannot explain the two different scales seen in this experiments. Okay. Then there's a second thing that this is actually known from BTK's time, and it's kind of simple if you think about it. If you have two different normal state dispersions, for example, if the Fermi velocities of the two underlying metals are mismatched, this leads to an effective scattering between the two. So even if I put a barrier which has no reflection, no scattering potential, there will be an effective scattering. You can think of it as an impedance mismatch. You can think of it how reflection of light occurs, etc., etc. So even if you nominally create a ballistic junction, okay, your junctions, effective junctions between, let's say, a tungsten or a gold tip and a flat band superconductor will always be in the high Z limit, will never be in the ballistic limit. And the idea is that particles cannot conserve both energy and momentum as they go from one to other. You can quantify this exactly in some ways, and if you set this V, which is the scattering potential, to 0, you will still see that there is an extra piece which will give you a scattering from this junction. And if you calculate this answer for a Moiré graphene and a metal tip, depending on exactly which one you take, alpha is between 1/100 to about 1/5, depending on which ones you take. Either way, you will put these junctions in the high Z tunneling limit. So your Andreev experiments, which you were seeing, are not quite ballistic junction limits. They are effectively in the high Z or high scattering limit. Okay. So then the question was that why do we still see the difference? Experimental data is what it is. You do see two different scales, and what happens is the difference is that there is no physical boundary between the tip and the material here, where when you push it down, there is a physical boundary. And then if you have a nodal superconductor where the gap function changes sign as a function of momentum, then we know that for certain cases, if you put a boundary, you can put an Andreev bound state at the boundary. So what you are measuring is the density of states of the Andreev bound state here. Here there is of course no Andreev bound state, and that's why you are getting two different energy scales. There is some calculation done for different values of VFS over VFN. And so what it is it's not evidence for strong coupling. That doesn't mean the system is not in strong coupling. All we are saying is that the two different scales in Andreev and tunneling does not indicate any strong coupling physics. It is rather a strong evidence for having a nodal superconductor. So this was the first part, and we kind of explained why people were seeing two different scales in this. But let me go to the second part, which is I'm right now more excited about because this has been something we have been working on very recently. And this is the idea that can we probe the pairing symmetry of Moiré graphene superconductors? And the goal of this work is, can you constrain the pairing symmetry of the Moiré graphene superconductor given what you know from the experiments and a little bit of theory? Okay? But again, there's a lot of theory. We will take only the parts which are robust or has some experimental verification, and we will, as a result, leave out other theories which have not had experimental verification. Okay, and then the second part is, can we propose some conclusive tests which, like, our chair can go and do and measure and hopefully tell us what the pairing symmetry of these things are. Okay, so to do that, we start from the normal state. So we have, and we try to constrain our answers. So this goes back to the original question, what is the normal state that from which you are deriving this superconductor? And what was seen is there are things called incommensurate Kekule spirals. I'll tell you in a minute what they are. These were predicted by Hartree-Fock theory in these papers. These papers did DMRG, QMC. They kind of showed that what these guys were telling in mean field theory was correct. And it's stabilized by a very small amount of heterostrain, which is almost always there in the samples. More importantly, it was observed by STM. So what is Kekule spirals? These are inter-valley coherent states, which means on a graphene scale, there will be charge density oscillations from lattice side to lattice side in this famous Kekule pattern or √3 cross √3 pattern. And this was picked up in STM experiments. This is an experiment by Kim and others on the twisted tri-layer graphene. There's been similar experiments on twisted bilayer graphene, and both have seen this incommensurate Kekule spiral. What is a spiral? This is something that is happening on the graphene lattice scale. In addition, there is an incommensurate oscillation with a momentum scale Q, Moiré scale Q, which is 1 over the Moiré lattice spacing, which is much smaller. The Q is much smaller than the graphene Brillouin zones, and the corresponding wavelengths are much larger than the graphene lattice spacings. Okay, and so both of these have been seen in experiments. So we can start with this as a essentially a starting point. What does this give to me as a theorist? It tells me that the point group is basically just C2. We don't need to worry about 6-fold rotations, 3-fold rotations, etc. There's just 2-fold rotation about z-axis. This is also supported by transport data in normal state because people have seen what is called nematicity, that there is essentially only a C2 symmetry when you look at direction dependent transport data, both in tri-layer graphene and bilayer graphene. The spin structure is a bit more complicated. The original one proposed was what is called a singlet IKS. So what is oscillating as a Kekule spiral is the charge density, and the spin doesn't do anything. And this will basically tell me that I have a spin rotation invariance. Okay, and so when I look at my bands, there should be 2-fold degenerate bands which are just spin bands. Okay, we ignore possible triplet IKS not seen in experiments. This preserves time reversal. This you can rewrite as some effective crystal momentum are good, some modified crystal momentums are good quantum numbers. You can get a band structure, and if you do the band structure, the important thing is that what you end up is small hole pockets near the zone center or the gamma points, and these are your spin degenerate bands. So this is the basic underlying thing that we will start our calculations with. So and then what about the superconducting state? Well, in the superconducting state, we have this V-shaped spectra. This is a more recent data from Pablo's group, which is planar tunneling, not the STM, but again, it is showing a very nice V-shaped structure for the nodal. There is linear temperature dependence of superfluid stiffness, and there is unribbed bound states seen in Picard, all of which indicate a nodal. I should point out, as we were discussing with Anila, that there is now one at least set of data which sees a hard gap, but everything else tries to see, and everything else gets as a nodal superconductivity. So we will take nodal superconductivity as a given, and then if you do look at this, with these constraints, if you look at the order parameter, you will realize that the parity and spin rotation invariance, sorry, C2 and spin rotation invariance would mean that this object is either even parity when it's singlet or odd parity when it's a triplet. So if you have singlet pairing, time reversal will tell you that this phi naught is basically real. And then you can have a S wave and a D wave because you are around a gamma point. This is a natural thing to expand in. And if you have nodes, D wave should dominate if it is a singlet. Okay. If you take spin triplet pairing, you get this famous D vector, and time reversal will tell you dk is real and odd in k. If you put nodal constraint, this is a very, very important thing. If you just say that all three components of D has to vanish along a particular direction, you will see that you will end up with a D vector which is independent of k and a phi 1k which is essentially p wave. Okay, so before going, let me just say one thing. If you take a singlet superconductor, the spectrum is independent of the direction of B. It's whatever it is, but it's independent of the direction of B. Whereas if you have a triplet superconductor, this part, there's an extra piece which comes from the component of B, which is parallel to the D vector, so it cares about the D vector. So the first thing is, if Anindya, you are putting a Zeeman field, and whatever you are measuring is independent of the direction of, starts depending on the direction of the Zeeman field, we can throw away singlet. We can also throw away a triplet with a D in the Z direction. Okay? So what should we look at? And if you can look at the density or local density of states, if you have a singlet, you will see that the local density of states will be a constant, it will be proportional to B. If you have a triplet, it should depend on the D vector, and you get this nice things where you get a D perpendicular to B, you get point nodes and no change in the gap spectrum, and where D is parallel to B, you will get this. And depending on how much your inelastic scattering is, you will either see the Van Hove or not. Last one slide, this will be the last slide. You can do more than that. You can now create a tunnel junction barrier, and then you will get unrib bound states if you have a nodal superconductor. If you now put a Zeeman field and you had a singlet, the unrib bound states split, and the splitting is independent of the direction of the B field that you are putting in. If you have a triplet order parameter, you can see this is phi B, the direction between the D and the B, and your answers will keep changing with D and B. Okay, so there's a phase, in principle you should be able to do this, look with an STM and pick up that the splitting starts depending on the direction of B. So let me keep the final summary for you. I'm out of time, so I will stop here, and if there are any questions.
Thanks, Steve, for an excellent talk. Open for 2-3 short questions from the audience. Yes, please go ahead. Is there any mic?
So yes, so I went quickly, good. So this is what is happening when D is parallel to B, okay? Then you get the Bogoliubov-Fermi surface that you get, and because you get a Bogoliubov-Fermi surface, you get a constant density of states. And this is basically this red line, okay? When D is perpendicular to B, you don't get this. You are actually, the single node splits into 2 point nodes, right? And there are 2 Dirac. So in between, of course, there is a Van Hove because you are just going up and then coming down. At some point, you will have to have a Van Hove. And basically, in this case, there are no Van Hoves. There's just 2 Dirac points, and that gives you this one. And any other direction, you start developing. These 2 are the Van Hoves, and these 2 are the Dirac nodes. So you see something which is going up, then there's a Van Hove, and you basically go back to the long-term answer. So yes, it depends on the direction between D and B. Yeah. Yeah, yeah. But the point being, this is a weak Zeeman field answer, right? So these scales are very low, and for realistic systems, you will have, so what will happen is this, what we have done is put different times broadening, and if you have reasonable scattering, etc., you may not be seeing this, but you will definitely see that it starts filling up as a function of direction. So the claim is if you have a triplet and you keep moving it like this, you will see that your density of states is filling up as you change your direction of the. You should be. Well, we were focusing on what they can measure.
So,
Yeah.
quick question. So, the same doping has IKS at high temperature and lower temperature has superconductivity, or
Yeah.
different dopings?
No, the same dopings.
So, the IKS is not fully gapped. It's because if it is fully gapped.
So the nu equal to 2, the IKS is fully gapped.
But then how do you get superconductivity?
But then you have bands still, right? So you're doping those bands. So superconductivity doesn't start at nu equal to 2. It's like, some 2.2, 2.3. So you have bands with a band gap. And then as you are going into 2.1, 2.2, you are doping these bands. Now, question is, what are the degrees of freedom that you are doping into? What is that band? The claim is it's already intervalley coherent.
Another quick question on the first part. So this two scales, experimentally, how does it evolve across TC? Like if I increase TC.
This, you mean
The two scales of the channeling and
so this does, I have not put the figure here. If I remember correctly, one goes something like this, and the other goes something like that as a function of temperature. They merge at some lowish temperature. And then fitting errors, factor of 2, it depends on how much you trust those extractions. Yeah.
Okay, let's move on because there's an organizer
Sure.
asking to move on. So let's thank
Sure.
Razdeep very much for the talk. Let's move on. So our next speaker, Professor Atikul Rahman, and he will be from my student. And
This is from your, okay, sorry.